we continue from, so this is a continuation of lecture 15, part 2. Okay, so last time we have seen how to find annihilators of functions, and now we see how to use annihilators to find solutions of non-homogeneous equations. Okay, so we have a non-homogeneous equation, say the nth derivative of y plus a1 of n minus first derivative plus up to an y equals b of t. And we denote this equation by pv of y equal to b of t. So pv is the differential operator, d to the n plus a1 times d to the n minus 1 plus up to an. Okay, so now if the function b of t has annihilator, say LD, when we apply LD to both sides of our equation, we get, so we apply LD to the left side of the equation and also to the right side. But LD is an annihilator of b of t, so the right side is going to be 0. So we have homogeneous equation in this case. LD PD of y equal to 0. Okay, so how we know how to solve homogeneous equations. We write the characteristic equation. So in the differential operator, instead of d, we put lambda to get our characteristic equation equal to 0. So in this case, the characteristic equation is going to have two factors, L lambda and P lambda. Now, when you set P lambda equals 0, this gives solutions, say y1, y2, up to yn of the homogeneous equation PD of y equal to 0. So this is the corresponding homogeneous equation of our differential equation PD of y equal to b of t. So these functions gives us the solution of the homogeneous part. So c1 y1 plus up to cn yn. Okay, so remember, to write the solution of the differential equation, first we need the solution, general solution of the corresponding homogeneous equation. I'm sorry. And then we need a particular solution. Now, for the particular solution, we look at the second factor in the equation. Remember, we have the equation L lambda P lambda equals 0. And now we use the second factor, L lambda equals 0, gives extra solutions. Y, say m plus 1 up to, say, m plus k. Okay, now these are going to be, this extra solutions are going to form our particular solution. So the first n solutions coming from P lambda equals 0 gives us the homogeneous solution, and the extra solutions gives us, so particular solution, C m plus 1, y m plus 1, up to C m plus k, y m plus k. But you don't need to make this distinction. So which one is P lambda, which one is L lambda? So you just write the solution of L d P d of y equal to 0 is, solution of this is, so we use all the solutions, y1 up to yn, and then ym plus 1, ym plus k. So the first n is going to be homogeneous, and the rest is going to be the particular. But as I said, you don't need to make this distinction. When you're working an example, you don't need to make this distinction. At the end, you will see which part is the homogeneous, which part is particular. How? You use all solutions to this equation. You write your solution in this form. Now plug this into our original equation, PD of y into bt, to find the coefficients of the particular solution of y, and this means of yp. So you don't need to say this is my yp, this is my yh, and just I'm going to find these constants. Take the whole thing, plug into the equation, and when you plug it into the equation, you will see some of the constants are going to disappear. The constant corresponding to the homogeneous equation are going to disappear, and the remaining constants are going to be the coefficients of your particular solution. So this is still the method of undetermined coefficients. But we are just using a different method. Instead of guessing the form of yp and then plugging it into the equation to find the coefficients, we consider a more general form, and this is going to give us both the homogeneous solution and the particular solution. Now, let's see how to do this in an example. As the first example, I'm going to redo an example we did before when we learned the method of undetermined coefficients, and you can compare the solutions to see which one works best for you. So our equation is second derivative of y minus y equal to 6 times e to the 3t. Okay, so first we write our equation using a differential operator. So second derivative minus the function, that means our operator is d squared minus 1. So PD is d squared minus 1. Now, what is the annihilator of 6e to the 3t? 6 is just a constant. We don't have to worry about the constant. The function e to the 3t, the coefficient of t is 3, so that means it comes from the homogeneous equation where the root of the characteristic equation is 3. Or you can look at our table from the previous video, and or just think about it. Derivative of e to the 3t is 3 times the function. So from the first derivative, we need to subtract 3 times the function to get 0. So annihilator of 6 times e to the 3t is d minus 3. So we apply d minus 3 to both sides of our equation. But when we apply it to the right side, we get 0. So we have the homogeneous equation. This is equal to 0. So we write the characteristic equation, lambda minus 3, lambda squared minus 1 equal to 0. So I'm going to consider the part coming from the equation itself. Remember, coming from PD. So first, I consider the part coming from the polynomial of the differential equation, lambda squared minus 1. So from lambda squared minus 1 equal to 0, I get the solutions 1 and minus 1. And then from LD, lambda minus 3 equal to 0, I get the third root to be 3. So I write my solution as C1 times e to the t plus C2 times e to the minus t plus C3 times e to the 3t. Since it comes from P of d, this part with C1 and C2 is going to be our homogeneous solution, and the second part is going to be our particular solution. But as I said, you will see when you substitute this into the equation. So plug this into the original equation. Second derivative of y minus y equals 6 times e to the 3t. So in order to plug in, we need the second derivative. Let me write the function again. Take the derivative. Second derivative. So then the left side of the equation, second derivative of y minus y, second derivative is this. And then we subtract the function. So you see the parts with C1 and C2 cancels out. C1 e to the t minus C1 e to the t cancel out. C2 e to the minus t minus C2 e to the minus t cancel out. We are left with 9C3 minus C3, so 8C3 e to the 3t. And we want this to be equal to 6e to the 3t. So the constant C3 should be 6 over 8 or 3 over 4. So we just find to figure out the constant C3. So in order to be a solution of our differential equation, the constant C3 must be 3 over 4. A general constant doesn't work. Remember, in the particular solution, general constant doesn't work. We need to find a specific constant which works for the equation. And in this case, it is 3 over 4. So our solution then, the homogeneous part, C1 e to the t plus C2 e to the minus t. And then for C3, we figured out that C3 is 3 over 4 e to the 3t. So this is our solution. And compare it to the solution we did before. I guess, I hope, I think we obtained the same answer. Okay, so you see, when you plug this general form into the equation, some constants disappear. So disappearing constants correspond to the homogeneous part, and some constants stay. So you work out your equation to find those constants, and those constants correspond to your particular solution. Okay, now let's work out another example. And in this case, let's make it an initial value problem. Solve the initial value problem. Third derivative of y plus 4 times the first derivative equal to t. Y0 equals 0. Y prime 0 equals 0. And y double prime 0 equals 1. Now the equation is a third order equation. So in order to find a unique solution, we need 3 initial conditions. Third order equation, in the general solution, we are going to have 3 constants. To find our unique solution, we need to find those 3 constants, so we need 3 conditions. That's why we have the function, the derivative, and the second derivative at the same point t0, which in this problem happens to be 0. Okay, so what we do, we first, we need to find the general solution first. So we write the left side using a differential operator. So third derivative, meaning d cubed, 4 times the first derivative, meaning d of y. And for the function on the right side, we need to find annihilator of t. This is t is a polynomial. First derivative is 1, second derivative is 0. So annihilator is taking the second derivative. So we apply the annihilator to both sides of our equation. But when we apply it to the right side, we get 0. So we have the homogeneous equation, d squared times d cubed plus 4d equal to 0. So we have the characteristic equation. To find the solutions, we need to consider the characteristic equation. Lambda squared times lambda cubed plus 4 lambda equal to 0. So again, first I'm going to consider the piece coming from p lambda, coming from the original differential equation. So lambda cubed plus 4 lambda equal to 0. If I factor out lambda, I have lambda times lambda squared plus 4 equal to 0. So the first root is 0. And for the second and third root, from lambda squared plus 4 equal to 0, I have lambda squared equals -4, so lambda is plus or minus 2i. I have complex solutions. So lambda 1. Since I have complex solutions, complex roots, how do we write the corresponding solution? The complex roots have no real part, and the imaginary part is 2. Okay, let me write lambda 2 is 2i, and lambda 3 is minus 2i. So how do we write the corresponding solutions? For lambda 1 equals 0, the solution is e to the 0 times t, so e to the 0, which is 1. So the first solution is constant 1. A second solution and the third solution comes from the complex solution, plus minus 2i. So real part is 0, and imaginary part is 2. So we have e to the 0 times cosine 2t, and e to the 0 times sine 2t, and e to the 0 is 1. So the second and third solutions are cosine of 2t and sine of 2t. And now we consider the remaining part, lambda squared equals 0. But of course, this has only one solution, 0. I have, since it's square, I have two solutions, lambda 4 equals 0, and lambda 5 equals 0. Because lambda 1, lambda 2, lambda 3, I get from the first part. So from the second part, I get, again, 0, 0. Now, how do I write the solutions corresponding to these roots? Now, to 0, we usually write e to the 0, which is 1. But we already considered that for lambda 1. So lambda 1, how shall I put this? So we already considered lambda 1. So for lambda 4, so 0, when you consider the whole equation, for the whole equation, lambda equals 0 is a root with multiplicity 3. Okay, so the first one, I have the solution, constant solution 1. For the second 0, this lambda 4 is the second 0. For repeating roots, remember, to get the other solutions, we multiply by t. So we multiply the first solution, which is 1, by t. And for the next one, it is again 0. So this is the third 0. We multiply with another t, we get t squared. You don't need to order them like this. I order them this way so that in the general solution, the first part with constants, we have the homogeneous part, and the remaining part, we have the particular solution. So that's why I separate the part coming from the equation itself and then the part coming from the annihilator. But when you're working out the example, you don't have to order your constants in this way. You can order them in any way you like. And once you plug it into the equation, you will see which ones disappear and which ones remains so that you can figure them out. Okay, so the general solution then y, c1 times the first function, constant 1, plus c2 times cosine of 2t, plus c3 times sine of 2t, plus c4 times t, plus c5 times t squared. So we need to plug this into the original equation. That means we need the third derivative. So the first derivative, minus 2 c2 sine 2t plus 2c3 cosine 2t plus c4 plus 2c5t. The second derivative, minus 4c2 cosine 2t minus 4c3 sine 2t plus 2c5. And the third derivative, 8c2 sine 2t minus 8c3 cosine 2t. Derivative of c5 is 0. So plug into the equation the third derivative of y plus 4 times y prime equals t. So I have third derivative of y, 8c2 sine 2t minus 8c3 cosine 2t plus 4 times y prime, derivative of y prime, minus 2c2 sine 2t plus 2c3 cosine 2t plus c4 plus 2c5t. So when you simplify, 8c2 sine 2t minus 8c2 sine 2t cancels out, minus 8c3 cosine 2t plus 8c3 cosine 2t cancels out, which is to be expected again because those functions are solutions of the homogeneous equation. So when you plug it into the equation, we obtain 0. Then we are left with 4c4 plus 8c5t, and it should be equal to t. That means the constant 4c4 should be 0 and 8c5 should be 1. So the constant c4 is 0 and the constant c5 is 1 over 8. So the solution, you see c1 also disappears from the equation because that also corresponds to, c1 also corresponds to the solution of the homogeneous equation, as c2 and c3 also disappear, so they have to stay in the general form of the solution. The constant c4 turns out to be 0 plus the constant c5, so plus 1 over 8t squared. So that's the general solution. Let me see if I did this right. 1 over 8, yes. Okay. So this is the general solution of the equation, third derivative of y plus 4 times the first derivative equal to t. Now, use the initial conditions. Y0 equals 0, y prime 0 equals 0, y double prime 0 equals 1 to find the constants C1, C2, C3. Okay, so first y0 equals 0. So I substitute 0 for y and 0 for t in the general solution. So when you substitute t equals 0, you get C1, cosine 0 is 1, so plus C2, sine 0 is 0, and t is 0. So we have C1 plus C2 equal to 0. To use the second condition, first we need the derivative of y. Derivative of y is minus 2c2 sine 2t plus 2c3 cosine 2t plus 1 over 4t, right? So derivative of y at 0 equals 0. So that means we put 0 for y and 0 for t. Sine t is 0. Cosine 0 is 1. So we have 2c3 plus t is 0. So we get 2c3 equals 0. So that gives us c3 to be 0. And finally, to use the last condition, we need the second derivative of y. Second derivative is equal to minus 4c2 cosine 2t minus 4c3 sine 2t plus 1 over 4. Second derivative at t equals 0 is 1. So we put 1 for y and 0 for t. Cosine 0 is 1, so minus 4c2. Sine 0 is 0 plus 1 over 4. So minus 4c2 is 1 minus 1 over 4, which is 3 over 4. So c2 is minus 3 over 16. And use it in the first equation. C1 plus C2 equals 0. So C1 is minus C2. So C1 is 3 over 16. This is C1. So that means, oops, I'm sorry, one moment. Okay, so I have the general form and general form of the solution, and we use these constants, C1, C2, C3, that we figured out to get our unique solution. C1 is 3 over 16. C2 minus 3 over 16. And C3 is 0. Remember, we also have plus 1 over 8t squared. So this is our unique solution of the given initial value problem. And let me check if I have this right. Yes. And that's all for now.